stochastic optimization for regularized optimal transport.
Thank you for the introduction and for the invitation to this workshop, which sadly isn't happening in person, but I'm still enjoying all the good, nice talks about optimal here. So what I'm going to talk about today is a mix of older work from my thesis that I did at ENS with Gabriel Perret, and also more recent work that I did here at MIT with Justin Solomon, Ling Shaoli, and Misha Yeroshkin. And so it's a nice way to connect to different parts of my work, and it both revolves around the idea of using stochastic optimization methods to solve problems that involve regularized optimal transport. So first, I'm going to show how the regularized optimal transport problem can be rewritten as a stochastic optimization problem, which is the basis of the rest of the talk. So I'm not going to reintroduce optimal transport because I think many people have already done so, but I'm at least going to reintroduce the regularized Wasserstein distance, which is the cornerstone of our approach here. So instead of looking at the usual Wasserstein distance, which would be what you have just here on the first line, so looking at the infimum over the space of couplings with marginals mu and nu of the integral of that cost function against that coupling, so that would be just a standard Wasserstein distance. Instead, we're adding a regularizing term here, which can be any convex regularizer, convex regularizing function with domain R plus. And so we're regularizing with respect to the product measure of the marginal. So here pi is the optimal coupling we're looking for, and we're regularizing with respect to the coupling mu times nu for our marginals. And so there are two main choices, two natural choices for the regularizing term here. The first one is the entropic regularization, which is very popular, especially in the machine learning community. It was introduced, or at least popularized by Marco Couturi in 2013, and it consists of using this function as the penalty. And so it's essentially amounts to regularizing with the Kullback-Leibler divergence of the transport plan with respect to the coupling. And the other possible regularizer, which we'll look at, is the quadratic regularizer, which looks like that. It doesn't have as many nice properties as the entropic regularizer, so it hasn't been as widely used, but it also has some interesting properties that I'll share more later. And so the reason why we choose to focus on these two regularizers is that it's easy to compute the dual problem for these regularizers, because we can we know their Legendre transform, and they provide a nice dual problem. So here is what you obtain when you take just the convex dual of the regularized Wasserstein distance. So we went from optimizing over the space of couplings with marginals mu and nu. So it was a constrained problem because the coupling had to have two fixed marginals. And so each of these constraints has a Lagrange multiplier. So F is going to be the multiplier for the first constraint, and G the multiplier for the second constraint. And so now we're optimizing over the space of continuous functions for two dual functions or dual potentials F and G. And so we have this, this first part, which is similar to the unregularized case, but then the fact that we are regularizing adds this, this term to the dual problem. And so the way you can understand this term here, which involves the Legendre transform of the regularizer, is that instead, so in the unregularized transport case, here you would have the dual of the Wasserstein distance would be this soup over F and G, constrained by the fact that F plus G must be smaller than C. So F plus G should be smaller than C. And instead of having this hard constraint, when we regularize, we are penalizing this constraint. So it's the entropic or quadratic regularizations can be seen as a relaxation of the constraints on the dual problem. And so now we have an unconstrained maximization problem over these dual functions. And we're maximizing now a concave function, which is smooth. And so we went from a pretty hard problem to a much simpler one, and that's the main benefit of using this regularized Wasserstein distance. And so if you take a look at this problem, you can actually rewrite it as the soup of an expectation over the product measure, right? Because here you have the integral against mu, here the integral against nu, and here the integral against the product measure. And so you can just rewrite it more generally as the expectation under the product measure mu times nu of this function. That also here involves the Legendre transform of the regularized. And here, so if you have x that are sampled from mu and nu and y that are sampled from nu, you are solving the maximization of an expectation of a smooth function here. And so what is nice about this formulation is that you can now resort to stochastic optimization methods to solve your optimal transport problem. And so there are many efficient algorithms to solve regularized optimal transport. So that probably the best known one is Synchron algorithm that was popularized by Marco in his entropy regularized transport paper. But the main drawback of using this Synchron algorithm is that it's fundamentally a discrete problem. So if you want to solve optimal transport with this Synchron algorithm, you first need to discretize your measures mu and nu, and then solve optimal transport on these discretized measures. So you introduce a discretization bias because you have to sample your measures a priori and then solve your problem in a batch way. So you first sample a lot of points, and then once you have sampled, you solve your problem. The nice thing about stochastic optimization methods is that they are fully online in the sense that at each iteration of your algorithm, you draw new samples from your measures mu and nu, and you do a gradient step thanks to these new samples. And at each iteration of your algorithm, you can use new samples of mu and nu, and so you get a solution that improves over time. And you can just, if you have a streaming input samples, you can just improve your estimation of optimal transport over time. Okay. So the problem, if we want to use gradient descent, is here our maximization problem is over the space of continuous functions. So how are we going to do a gradient descent over the space of function? Well, the idea here is to replace the dual potentials f and g by their expression in a well-chosen reproducing kernel Hilbert space. And we will then do gradient descent on that reproducing kernel Hilbert space. For that, I'm going to first recall the definition of a reproducing kernel Hilbert space. So we say that a Hilbert space H with a certain kernel function K, that is a positive definite symmetric function, is a RKHS if and only if the kernel function kappa belongs to that RKHS. And for all functions in the RKHS, you can write the function as the scalar product of a representer of that function against the kernel. So that's a very convenient property of RKHS, is that any function in that space can be decomposed as this scalar product. And so it makes a lot of computations much easier thanks to this structure. And so with this in mind, we will rewrite f of x as the scalar product of a representer f against the kernel, and similarly for g. And then we can plug these decompositions back in the dual formula here. So you just replace f by f scalar kappa, g by g scalar kappa, etc. And so you now have a maximization problem of an expectation of kernel functions, essentially. And now we can do stochastic gradient descent on these representers, f and g, instead of having to do stochastic gradient descent in the space of continuous functions directly. And SGD in the space in the RKHS is something that has been well studied and for which we have known algorithms and convergence results. So we can now use it for our regularized optimal transport problem. And so, as I said, the nice feature of this SGD algorithm is that at each iteration, we just need to draw a sample or a mini batch, so a small number of samples, X from alpha and Y from beta. And so it's a fully online algorithm. So each time we get new samples, we can improve our solution. Right, so if you write down the iterates in the RKHS, so if you actually compute the gradients, so it's exactly the same as doing gradient descent in a vector space, but you're doing this on the representers of the function. And so if you write the gradient iterates, you can actually summarize them as follows. So they're going to be the sum of some functions here, wi, against the kernel that is taken at the sample points xi that are sampled from alpha for f and from beta for g. And so that's, so it requires just some simple computations to arrive to this thing. But what f is here is really just a gradient descent step. Okay, fk is going to be fk minus 1 minus the gradient of the function that's that you're trying to minimize, and they can incidentally be rewritten in this very compact form here. That's nice to work with. And here the coefficients wi in front of the kernels also involve the previous iterates f minus 1 and g minus 1. Okay, so it looks a bit complicated when you look at it like that. It's not very intuitive, but essentially what you just need to understand is that you can rewrite your iterates in the kernel SGD as very simple sums of kernel functions, and the size of the sum here grows with the number of iterations. So at each iteration, you're adding a new term to this sum. And so we can actually prove that this kernel SGD algorithm converges in our case. So if we have measures that have bounded support in RD, then if we take kappa to be the matern kernel or a universal kernel, so for instance, the Gaussian kernel, then the iterates UK and VK converge to a solution of our dual problem, so the one we are trying to solve. So quick parenthesis, so what is a universal kernel? It's simply a kernel for which the RKHS is going to be dense in the space of continuous function. So it means that with this kernel, you can actually approximate any continuous function. And what is the matron kernel? It's the kernel that induces the RKHS, that is the one of Sobolev functions. And we can actually, why do we use this kernel is because we know, and we have proved that the dual potentials f and g have a certain smoothness and they're bounded in Sobolev norm. And so that's why if we do the kernel SGD either with the matron kernel or with a universal kernel, then we can prove that the iterates will converge. So here is an illustration of the algorithm. So it's a very simple setting in 1D. But here you have two Gaussians, and here is a convergence of the one of the dual potentials that we computed. So we computed the optimal dual potential by oversampling a grid, so it's in one dimension. So sampling gives normally pretty satisfactory results. And so here in red would be the dual potential that you're trying to, so the optimal dual potential, and here in blue is what you get with the iterates of kernel SGD. And so the darker the blue, the more iterations you do. So you can see that as you start, you're pretty far from the optimal potential, but the more iterations you do, you're actually really converging to this red line here. The drawback of this kernel SGD, however, is that it's very slow. So at each iteration k, as I said, we need to compute this sum of kernel functions. And so I said this sum has the size of the number of iterations. So the more iterations you do, the bigger this sum gets. And so the iteration k is going to cost you O of k. So that's and this algorithm actually needs a lot of iterations to converge, so it quickly becomes intractable. So the idea that you can use to accelerate this algorithm is to use an approximation of the kernel function. So instead of using the kernel here, to either the Gaussian kernel or the Matroon kernel, in practice, we will use the Gaussian one because it's easier to compute. But we're going to replace this kernel by a scalar product. So it's an approximation that we can do either with the Cholesky decomposition or the random Fourier features. And so this allows you to decompose the kernel as a scalar product of two feature vectors that are in some space here Rp. So you can choose the P that you want here. So of course, this will, if you take P to be very small, you'll lose precision, right? Because you're going to have a poor approximation of your kernels if you choose small dimensional vectors here. So this is also a parameter of the algorithm. But once you replace your kernel here by this scalar product, you can actually get a much more simple formulation for these iterates. And then each iteration is going to have a fixed cost that is going to be O of P, where P is the dimension of your feature vector. So you have the cost of an iteration that is independent of the of that iteration. Okay, before iteration K costs O of K, and no iteration K costs O of P, which is independent of K. And so as you can see, this brings a very significant speed up. So here we compare different approximation methods. So as I mentioned, you can either use random Fourier features or Cholesky decomposition. And here is the fact. So here in orange, you can see the standard kernel SGD, whose iteration scale, for which iteration K scales as O of K. And here you have the approximation methods who have a cost that is independent of the number of the iteration. So you can really see it on this graph. And here on the right, so you can see that both random Fourier features and Cholesky decomposition have a similar CPU time, but it's much, much better than the classic kernel SGD. And here on the right, you have a comparison of the precision of the algorithms. So you can see that, so here, these two are Cholesky decompositions, which tend to be not very efficient methods here. They don't provide a very good approximation. If you want to compare, so here's the convergence curve in orange of the classic kernel SGD. So we want to be able to do as good as kernel SGD. So you can see that it's not the case for Cholesky decomposition. If you take random Fourier features, but you take your feature vectors to be in a small dimension space, so in 5 dimensions, you lose a lot of information. But if you take random Fourier features that have enough information, so that are in higher dimensional space. So here, for instance, in dimension 20, you don't really lose any information, and your convergence curve is the same as what you would get for the classic kernel SGD. However, if you do, for instance, 10 to the 6 iterations, kernel SGD is going to take 6 hours, which is unthinkable. But if you take random Fourier features with dimension 20, it only takes 3 minutes. So the speed up is really considerable, and you don't lose anything in terms of precision. So if you want to use kernel SGD, then doing this kernel approximation using random Fourier features is really instrumental to have an algorithm that, that can be useful in practice. So note that we have designed a stochastic algorithm to solve optimal transport in an online and efficient way. We can know, without relying on a discretization scheme for the measures, now we can try to apply this to the problem of Wasserstein barycenters. So the motivation here to use this stochastic optimization method is to do Wasserstein barycenters without having to discretize the support of the barycenter. So Elsa yesterday already gave us a talk on Wasserstein barycenters, so I don't have to remind you of all its motivations. But here, what we want to do so why we were interested in solving this problem is that we wanted to be able to aggregate probability distributions, which is always the motivation for Wasserstein barycenters, but without having to discretize the inputs. And what we assumed was that we had sample access from the different sources, mu1 to mu_n. And so we're going to use the dual formulation of the regularized Wasserstein barycenters, and then parameterize the dual potentials and solve it with SGD. So the approach is very similar to the approach we used for optimal transport, but for Wasserstein barycenters. So just to recall what are Wasserstein barycenters, so they were introduced by Haguet and Carlier in 2011, and so you take n input measures, so n input probability measures, and so you want to compute their average in the Wasserstein sense. And we say that a measure nu is the Wasserstein barycenter of mu1, mu_n, with weights λ1, λn. So if we want to compute the standard average, we're just going to take λ1, λn equals 1 over n. If mu solves this minimization problem, so the infimum over all probability measures of the sum of the Wasserstein distances between mu I and nu, where W here is the Wasserstein distance between mu I and nu. And so here we have an infimum over the barycenter measure nu, but here the Wasserstein distance is itself already a minimization problem over the space of couplings. So that's why it's a particularly difficult problem, right? Because you're solving a minimization problem here, but all these Wasserstein distances here are already minimization problems that are quite costly to solve. So to obtain a more efficient algorithm, so the idea is to regularize. So there are already several Wasserstein barycenters algorithm which rely on regularization, but the way ours is specific is because it deals with continuous measures. So the formulation for regularized Wasserstein barycenters is very similar to the unregularized one, right? Except we replaced the Wasserstein distance here by the regularized Wasserstein distance. And here, this index here means that instead, so in the usual regularized case, we would regularize with respect to the product measure mu I times nu. That's what we did when we were looking at optimal transport, right? We were looking at the regularization with respect to the product measure, but here nu is actually what we are looking for. So since we don't know it, we can't use it in the regularization term. So instead, we choose some reference measure. So there's a notation. Yeah, right. So instead, we choose it to be a uniform measure over the support of the mu i's. Because we can't, in an ideal case, we would like to use nu, but we don't know it because that's what we were looking for. So we need to find a proxy for it, and we choose the support of the input measures here. Right. And so now, thanks to the regularization, we have a nice dual formulation for the Wasserstein barycenters, and it looks a lot like of course, like the dual formulation of optimal transport. And so it's actually a sum yes, it's a sum of functions here that involve potentials Fi and Gi for each sub problem with measures mu I and nu. And so you can see that in the dual, so here we were looking for an infimum over the barycenter measure nu, and now we're looking for the supremum over couples of potentials Fi Gi for I from 1 to n. So you have a potential, you have potentials for each of the pairs mu I and nu. And here it's a constraint problem, so we need to constrain the sum of the GIs to be equal to, the weighted sum of the GIs to be equal to 0. And here again, you have the Lagrange transform of the regularizer that is in this dual formula. And so what we can prove is that for this problem, strong duality holds. So it's actually equivalent to solve the primal problem and this dual problem. And moreover, if a couple FI-GI solves this regularized dual problem, then it is also a solution of the optimal transport problem between mu I and the target barycenter measure nu, right? So each of these solutions, so the solutions to each of these sub transport problems are the solutions of this dual problem are each solutions of the sub optimal transport problems between each of the source measures mu I and the target barycenter measure nu. So similarly to what we did for optimal transport, we can rewrite this as a stochastic optimization problem. And here the expectation, I forgot to write it down, but it's with respect to the product measure, again, of the input measure, of the input measures and the target measure. So each of the xi will be distributed according to mu I, and the y will be distributed according to our regularizing measure eta. So it's written here. So at each iteration, we will take samples from each of the sources mu I, and we will take samples from our regularizing measure eta that we chose to be a uniform over the support of these mu i's, as I said before. And another trick that we need to use is to enforce. So we had this constraint that the weighted sum of the GIs had to be equal to 0, and we enforce it by replacing GI by GI minus the sum of the other G's to ensure that that its average is going to be equal to 0. And so now we have rewritten our regularized Wasserstein barycenter problem as a stochastic optimization problem. And we're going to be looking again at supremums, at the supremum over continuous functions that are the dual potentials. And so again, the technique is similar to, so here's Genevet, Couturi, Perret, Bach from 2016. So it's the paper in which we introduced this stochastic optimization idea for optimal transport. And so that's what we use to solve this Wasserstein barycenter problem. So we parameterize the dual potentials Fi and Gi using either random Fourier features or neural networks. So the idea of using neural networks to parameterize the dual potential is due to a paper by Vivien Segui and co-authors, which was essentially an extension of the stochastic optimization method that we introduced, but where instead of using the kernel formalism, they used the neural network framework to solve their problem. And so once you parameterize your dual potentials here, you can just solve with SGD. So either in the kernel case by formally computing the gradient, or if you're using neural network, you can just use automatic differentiation to compute the gradient of that thing with backpropagation. Okay, so our algorithm is going to give you the dual potentials here, Fi and Gi, but what you want is to have the actual barycenter measure. So how do you recover the barycenter measure once you have solved the barycenter problem? Okay, so thanks to the primal dual relationship, so in the dual problem, we were computing the dual potentials Fi and Gi, and in the primal problem, we were looking at the optimal transport plan pi I. So if you look at the primal dual relationship, it tells you that you can write the optimal transport plans pi I as some function here, pi, with respect to multiplied by the product measure of the source mu I and the regularizing measure eta. And so the pi here is going to have a different expression whether you're using entropic regularization or quadratic regularization, but they look very similar here. They involve here the sum of the dual potentials minus the cost function. So this primal dual relationship gives you the optimal transport plan from the dual potentials, and know how to access the barycenter. So there are two ways we want to be able to access the barycenter. One is to visualize it if we are in small dimensions. So if we have images, we want to be able to visualize the barycenter of these images. The other thing is being able to obtain samples from this barycenter. So if we are in higher dimension, we can't really visualize the barycenter, but we want to be able to sample from it, for instance. So there are two main classes of recovery methods. So the first one requires to have known input densities. So if we know the density of the mui's, the first thing you can do is to do numerical integration. So you discretize your space, and then you approximate the barycenter measure by taking the marginal of your transport plane. So you know that your transport plane solves the optimal transport problem between your source mu I and your target, which is the barycenter nu. So if you want to get the density of the barycenter nu, you just have to marginalize your transport plane with respect to that second coordinate. Of course, numerical integration is something that's quite expensive because it requires discretizing your space and having a fine grid, so it's only tractable in low dimensions. The other thing you can do is using MCMC methods. So if you have a density for pi I, you can sample according to your transport plane pi I, and then take so pi I is going to be a coupling between mu I and nu. So you sample according to this coupling, and you're going to get samples that are distributed according to mu I times nu. And then you just take the second component of the samples to get samples that are distributed according to your barycenter nu. So that's for the first class of method. The other more general class relies on computing Mulch maps. And so Mulch maps are the solution to this Mulch problem, which is an equivalent formulation of optimal transport, which requires that actually Elsa mentioned yesterday also. So instead of looking for couplings, which is the Kontorovich formulation, you're looking for Mulch maps here, T, that will push forward mu into nu. So they transform your first measure mu into your target measure nu. So the reason why we don't use the Mulch problem in practice is because this constraint is very complicated to enforce. But the idea is that you want to have some map T that takes all your samples from the first measure and transforms them in the samples from your other measure. And so if you have a sample X from mu, you can get then a sample Y from mu by using this formulation Y equals T of X. So it's just really a function that is going to transform your first measure into your second measure. So there are several ways to approach this the solution for Mulch maps. The first one is to consider the barycentric projection. So that's what they do, for instance, in Vivian Segui's paper. So if you take your cost function in optimal transport to be the squared Euclidean distance, then the barycentric projection has a much simpler form. And so you can just take your Mulch map between mu I and nu, so your Mulch map Ti, to be the expectation of Y with respect to the conditional coupling pi I. So that's one way to compute the Mulch map. The other one, which is very simple, is to take the gradient of your dual potential. So this formula is normally only adapted to the unregularized case. So it tells you that if you have your cost that is the squared Euclidean distance, so it's for the same cost here, then you know that your transport map between mu I and nu can be rewritten as x minus half of the gradient of the dual potential for that optimal transport problem. So since in our with our SGD algorithm, we compute the dual potential Fi, we can very easily then, using the gradient formula, recover this Mulch map formulation. Of course, since what we compute in practice is a regularized potential, it's not very rigorous, but it's we'll see that in practice it works pretty well. And then the last way to compute the Mulch map, which is the most expensive one in a sense, because we need to solve another minimization problem. It's also something they propose in Segui's paper. So not in the case of barycenters, they use it for just to learn optimal transport map without barycenters. So you parameterize your transport map. So for instance, by a neural network function, and then you solve the Mulch problem. So you sample according to your optimal coupling that you compute beforehand, and then you solve. So you first need to solve the barycenter problem to compute the BiIs, and then once you have the BiIs, you sample according to it, and you solve this other minimization problem using again stochastic gradient descent, where you do the descent on the parameters of the Mulch map T. But you can see, since you need to solve an extra minimization problem, it's going to be a lot more costly in practice. Okay, so I'm going to finish with some numerical results for these barycenter methods. So first, let's compare the influence of the regularizers. So here we have two, at the top, you have two images from the MNIST data sets. So two 3 digits. And we want to average them in the Wasserstein sense. So here on the left is what happens when we use the, so L2 is the quadratic regularizer. You can see that if you take, so epsilon is the strength of the regularization. So the smaller epsilon, the closer we are to the true optimal transport. And so you can see that if you regularize too much, so if you take a regularization parameter that's too large, you get something that gets very blurry. But as you decrease the regularization parameter, you get something that looks much nicer. So of course, this regularization has a smoothing effect. So here you can see if you regularize, if you take your regularization parameter to be very small, you get an average that is that starts getting a bit not very elegant. So you can see that a bit of regularization is actually gives you a smoother, nicer average. And here, this one is the entropic case. So for the entropic case, we can't take a regularization parameter that is too small because due to the exponential in the entropic regularizer, we have numerical stability issues. And so you can see that the regularizer we get with the, that the average we get, the barycenter we get with the entropic regularizer is very, very blurry and not very satisfactory. And here is a comparison of the parameterizations. So as I mentioned, you can either take random Fourier features or take neural networks to parameterize your barycenters. So the nice thing with random Fourier features is that they have a nice theory behind them. You can actually prove convergence results with random Fourier features. It's not really the case for neural networks, but you can see that neural networks work really well in practice, while random Fourier features will be more sensitive to the parameters inside the kernel. So when you do random Fourier features, so here we did it with a Gaussian kernel, and so the Gaussian kernel has a bandwidth parameter. You can see that depending on the bandwidth parameter that you choose, you can either get a good result here or something that is not as good. So for simplicity of use, we in the rest of the experiments, we used a neural network parameterization. Okay, so here is a comparison of the different recovery methods that I mentioned on a variety of problems. So here you have the first line is the average of a square and a circle. Here is again the average of 2 3s. Here's the average of 3 ellipses, which is very popular in the barycenter papers. Here are 2 rectangles, and here it's a 3D problem of 2 squares. So the first column here is numerical integration. So you can see that you obtain a very, very nice, very clean result because it's in 2D and small things. So you can discretize your space without too much, without going into too much trouble. Here, the second one is MCMC. So again, MCMC is fairly efficient in these small dimensions, but it's a pretty costly method. It takes a lot of time to converge, but it gives satisfactory results, albeit a bit blurry. Here is the barycentric projection from Segui's paper, which is not very satisfactory here. It tends to, I mean, it's a nice graphical feature, but it looks a bit like it's exploding everywhere. So it's not really what we expected from the barycenter. Here is the gradient of the potential method, which is probably which is the cheapest recovery method that we have. And for how cheap it is, it gives surprisingly pretty good results. We have some artifacts in places, but overall it's very satisfactory. And here is the method that computes the Mulch map by parameterizing it and solving another minimization problem. So overall, I would say this method is really good in small dimensions. It gives really nice visual results. So if you want to average images in 2 or 3D, that's probably the one you should be using. MCMC is a nice idea, but here it's not really useful. Barycentric projection doesn't work very well at all. The gradient of the potential is very satisfactory and very cheap. And this one gives similar results to the gradient of the potential, but at a much higher computational cost. Okay, so now that we have kind of seen what methods worked well on toy problems with images, we can use it to solve barycenter problems on things that are actually continuous. So here we're going to start small with Gaussians. So in the Gaussian case, what is nice is that we know that barycenter of Gaussians is a Gaussian, and so there you can obtain the parameters of these Gaussians with a fixed point algorithm. So it's this algorithm is developed in a paper from Alvarez et al. From 2016, and so we in this way we can get a ground truth for the barycenter of Gaussians and see if our method works well in that framework. And so we compare ourselves to a 2014 paper from Couturi and Doucet, and another stochastic optimization method, but that requires discretization from Clacy and the co-authors. And we can see that in small dimension, the Couturi-Doucet method is the one that gives the best performance, but in higher dimension, our method, so using the gradient of the potential and the L2 regularization, is the one that has the smallest error. And so the way we compute the error here is by looking at the norm of the estimated covariance, estimated covariance matrix of the Gaussian against the ground truth covariance from this fixed point algorithm. And so as we expected, since our method is continuous, so it doesn't require discretizing your input or output measures, it behaves better in higher dimensional settings, which tend to not react very well to discretization. And to finish, the application that essentially motivated our introduction of these continuous methods is doing Bayesian posterior fusion. So Bayesian methods represent their parameters by, when they do inference, they represent their parameters by distributions over the space of parameters. And so Bayesian inference is usually very expensive. So what you can do is that you can do Bayesian inference on subsets of the full data set, compute your Bayesian posteriors on these subsets, and then aggregate them using the Wasserstein barycenter. And of course, as the ground truth, we use the barycenter on the full data set. Here, the example that we chose was a Poisson model with 8 parameters. So we're doing the Wasserstein barycenter on an 8-dimensional posterior. Okay, so it's a fairly high-dimensional problem, so it wouldn't work well with discretizations or grids. And so that's where our method can be really useful. And so you can see that the number of samples that we use, so as as I said, our method relies on stochastic optimization. So at each iteration of the algorithm, we add new samples. And you can see that the more samples you add, the better the solution gets. And so the better our barycenter of the posteriors approximates the full posterior. So if we compare to this method of Coutouri and Doucet, the drawback of their method is that it doesn't scale well with the number of samples. So essentially that here 5,000 is the highest number we could use to have the algorithm run in a reasonable time, while our method can handle a lot more samples, and thus it can become very effective and approximate the Bayesian posterior, aggregate the Bayesian posterior in a more meaningful way than this discrete method. So that's that is all for today. So essentially, the take-home message here is that you can rewrite optimal transport. So if you take regularized optimal transport, you can rewrite its dual problem as the maximization of an expectation, and then it allows you to use stochastic optimizations method to solve it. For that, you need to parameterize your dual potentials, either with random Fourier features or with neural networks. And then this method also applies to other problems that use optimal transport, and in particular, Wasserstein barycenter. So this whole work on Wasserstein barycenter is a recently published paper with Justin Solomon, Ling Shaoli, who was the main author, and Misha Yurushkin. So you can find this paper on arXiv if you want more information. Thank you for your attention, and I'll be happy to answer questions.
Thank you.
Well, I have a question.
Yes.
Hi. Hi. Could you go to the 2 slides before this? So when you show like parallel 4 different methods, so you mentioned the first method, if I remember correctly, is the MCMC. So what is the drawback of this one?
So essentially, if I remember correctly, it takes a lot of time to obtain samples, to have the MCMC chain to converge to that distribution. So it works well, but it's just pretty slow.
Yes, I agree. Thanks.
Yeah, hi, I have a question as well. So first, thank you very much for your presentation. So with regard to MCMC, I'm pretty sure you're talking about the MCMC based on the random walk, right? Because there are other methods, for instance, MCMC based on the Craig-Nicholson proposal, which is much faster, and even it works in very high dimensions. For instance, in data simulation, is very useful when we work on with nonlinear observation operators. So basically, in this case, you're using just the random walk, right? So just maybe a normal distribution. You're using a normal distribution as your proposal distribution, and that's it.
Yeah, I think we just use like a classic Metropolis Hastings algorithm.
Okay. Yeah. Oh yeah, because there are other like MCMC flavors that are much faster than the traditional ones.
Okay. Yeah. Okay. Thanks. Yeah, we
were. No, thanks to you. Very nice presentation. Thank you.
Thanks.
Yeah, I also have a question. Yeah, thanks. I mean, this is all kind of quite interesting and promising for doing things in high dimensions. I was just wondering, how much does the choice of the RKHS influence kind of the results? Because, right, one would like, I mean, even though this is regularized transport, right, we know that, the transport, the Lipschitz functions would be kind of a natural choice for the transportation potentials, right? Because you can have the mass splitting, right? And, you were using Gaussians, right? So if epsilon is small, I think this would be difficult. Or if one is using neural networks, what particularly about the architecture, about, kind of what classes of functions are built to represent the transportation maps? Are these general neural network approaches at all adapted to working with optimal transport, or do the generic ones work just as well as anything?
Okay, so yeah, that's a good question. So there's several things I want to answer in your question. So first, for the RKHS, So one thing that we were able to prove in a separate work was that if you look at the dual potentials for entropy regularized transports, you can prove that their sub-F norm is bounded, and that the norm depends on the regularization parameter. So of course, the larger epsilon, so the more you regularize, the smoother are your dual potentials. And so the smoother they are, the better they are approximated with Gaussians. In practice, so even though the right kernel for these dual potentials should be the matterm kernel, so the one for sub-F spaces, it works fairly well with Gaussians, but it's quite sensitive to the choice of the bandwidth. I assume that if we took a very small epsilon, then it wouldn't work very well with Gaussians. As for the neural networks, so we used a very standard architecture. So it's Ling Xiao Li, our student who did the experiments. So I'm not really sure exactly what architecture he took, but he didn't take anything specifically tailored for neural networks.
Mm-hmm.
So it seemed to be fairly robust to the choice of architecture. However, I know some people have worked on similar things for using input convex neural networks, using the fact that you can say that your dual potentials are the gradient of convex functions. Sorry, that your transport map is the gradient of a convex function. And so that's one instance of using specific neural networks for optimal transport that I've seen. But in our setting, just a fairly standard neural network architecture gave really good results already.
And just a kind of follow-up question somehow, did you try any examples in kind of really high dimensions when maybe measures are supported maybe on a low dimensional set, but the ambient dimension is large, so that your space of function that you're using is actually now complicated and approximating by RFF is more difficult, say?
No, we haven't tried that, but that would be an interesting setting that we didn't really think of. I guess we didn't go much beyond dimension 8. I guess our main problem was trying to make sure that we had something for which we could have a ground.
Right. Well, 8 is already substantial, right? Yeah. I would say. Yeah.
Yeah.
Thanks.
Any more questions? So I welcome you to go to GatherTown to have further discussions that are less formal. Thank you all again.
Thank you.